and share my screen, and that's the right one. I will, so I have these three windows open here. I have the quiz here opened on the left-hand side. We'll be going down through each of these problems and I'll be annotating them, how you're supposed to annotate them for the answers. Again, no partial credits. You either will get full credit or no credits, depending on how you've annotated. And so you have to have everything exactly like I have it in order to get credits. On the right-hand side over here, we'll use the top window for our session 1 and the bottom window for session 2. So just to ensure that we're starting off with an empty problem here, I'm well, let's see, I'm in the SQL quiz folder. That's why there's this basket A and basket B here. But there's nothing else here, no table A's, no table B's. We'll start off with a create table T a int command here, this line 1 over there. Then line 2, create table U a int like that, and begin our transaction on line 3. Lock table T in share mode like that. And then down here on line 5 is where we're at. We will begin and then lock table U in share row exclusive mode. And at this point, we know there's been no possibilities that anything could block or deadlock because these lock commands are happening on two separate tables. And so things happening on separate tables never interfere with each other. We're at just completed line 7 and on line 8 now. Here, this is session 1. So lock table U in row exclusive mode like that. And here we have the possibility of the tables or the two sessions interfering with each other because we've already locked table U down here. And now we have to see, are we going to block or not block? And I'll hit enter, and you can see that the control flow does not go to the program. So we do in fact block here. And the instructions tell us that circle all SQL commands that block. This was line 8 over here that we typed in. So that one, you could circle the whole line, that's a circle, or you could circle the number 8, anything that's that thing right there circled, you're good. Now we're on line 9, locking table T in row exclusive mode. Lock table T in a row exclusive mode. And now there's three possibilities of what could happen. Either nothing will happen, or we could block, or we could deadlock. We know that we're not going to be blocking though, because if we're blocking, then we'll be deadlocking because each of these two sessions will be waiting on each other. So let's hit enter, and we can see that because it did block there, it leads to a deadlock. And so you write the word deadlock right here. And then it tells us to stop the problem. So this is a full credit answer for this problem. I guess if you were to have circled the locking here, because it does as well block as deadlock, that would be fine. That circle there around that command optional. Any questions about the first problem? Okay, so as a reminder, tomorrow there's the homework due on inserting into Postgres, and the inserting in the denormalized version is going to be really easy to make parallel. The inserting in the non-batch version of Postgres will also be easy to make parallel because the transactions are so small, they're not going to be interfering with each other at all. But the insertions in batch mode, they will have a lot of blocking and deadlock going on by default because of all these situations that we're going over in this quiz. The homework doesn't have these explicit locks anywhere, but it does have a lot of implicit locks. And so understanding what is causing the implicit locks and causing the resulting blocks and deadlocks and fixing that will be key to the homework. Problem number 2, question, yes.
That's due on the left,
right? Tomorrow? The 11th is next Tuesday. Is that right? Okay, then next Tuesday is when it is due. Yes. Apologize for the panics. Problem number 2. So here, no longer into the explicit locks, but some potentially implicit locks going on here. In order to reset this problem, let's just check our database here. We have this T and this U table. Let's drop table T and drop table U like that. Now their database is back in a clean state and we're ready to begin. I will go ahead and clear my screens again with the \bang command. In pSQL, you can run arbitrary terminal commands. A convenient terminal command is reset, which clears the screen and clears the history in your terminal as well. So we have a clean session now. Problem number 2, line 1, create table T, A, int primary key, D, E, F, I always misspell deferrable, DEFERRABLE, initially DEFERRED. There we go, no typos, excellent. That was lines 1 through 4. Now line 5, begin. Isolation level repeatable read. What do I have? Read. There's already a transaction in progress. Whoops, I didn't abort my previous transactions now. So there's still that things in the database drop table T, drop table U, and that's not a U, that's a U. And now I can rerun that create table command. And now we've actually run lines 1 through 4 up here, and on line 5, begin isolation, and I will do Control R, begin isolation level repeatable read, and there we go, that worked. So we've run lines 1 up through 6 at this point. Again, every time you're in a transaction, there are multiple isolation levels about those transactions, and they do have some potential weirdness that goes on with the update and delete commands. Anything that is accessing the contents of the tables and where the action that we're doing depends on the contents of the tables. But in this case, we're only running insert commands, so the isolation levels, just kind of a red herring here, not going to be important in any way. Line 7, insert into T values 5, insert into T values 5, like that, no problems. And then line 8, session 2 down here, begin and insert into T values 6, no problems. There we go. Line, that was 9, that insert right here. We're on line 10 right now. Insert into T values 6, and insert into T values 6. Here's the first command that might have weird interactions going on. Let's hit enter, and we can see that we do not block on this command right here. We do not block, even though there's a potential conflict on our unique constraint. We call it the primary key up here. Means that the integer A is both not null and unique. And so there is a unique constraint. And so there was potential to block because we are potentially inserting 2 6 values right here, but the deferrable initially deferred line right here says that we're not going to check this unique constraint until the commit line down here, rather than doing it on every individual insert command. So there's no annotations needed for line 10 right there. Line 11 here, select count star from T. The answer is 2. You should be putting a 2 about that line 11. And then line 12, insert into T values 5, insert into T values 5, like that. Again, there's no blocking going on. This 5 right here does not block with this 5 up here because of this deferrable initially deferred constraint. If we did not have this right here, if we did not have line 3 right here, then we'd actually be in a deadlock situation because both sessions would be waiting on each other. So this deferrably initially deferred is one of the strategies for avoiding deadlocks. So no deadlock here. Line 13, we abort this transaction, and then on line 14 up here, we commit that transaction, and no error messages, no blocks anywhere, everything was good. So a full credit answer is just putting the number 2 next to line 11. Any questions on this problem? Yes.
It's more just on like the so when I was working inside a transaction. And so if we do commit
If you commit to a table that you've already blocked, if you
drop, but not a command block for you inserting inside
so your suggestion is let's begin a transaction up here. Let's insert into t values 10 like this. And then you're saying down here, let's drop the table t. Is this the scenario that you're on? And here we are blocking on the drop table t because I believe this requires an exclusive lock on the table t. And up here, we've already acquired the row exclusive lock. And these two locks are incompatible with each other. So this one blocks waiting for this up here. And then it doesn't matter whether we commit or abort or roll back up here. That as soon as I commit this, there's no error message here because this transaction finishes before this line down here is able to even start. And then after this finishes right here, then this runs and drops the table, and now there's nothing in that table. Did that answer the question? Yeah. Okay, cool. Yes. Question is on line 13, what would have happened if we had a commit instead of an abort? And it would have, I don't think there would have been any problems at all. Let's double check that. Drop table T, I think we already have that, \d, \d. Recreate the table, re-begin my session, insert into t values 5 down here, begin, insert into t values 6 up here, insert into t values 6, select count star from t, insert into t values 5. And so I've run everything up to line 12 right here. And the question is, what if on line 13, instead of having an abort, I had a commit at this point? And then at the point of the commit is when it is going to check whether the constraints are satisfied or not satisfied. And I'll hit enter, and you see there's not an error message right here because it needs to check whether these constraints are satisfied or not satisfied, and it can't do that because of these locks that are the inserts over here on the left-hand side created. We don't know whether there's a 5 and 6 in the table yet. So if this were commit, it would be blocking. And then on line 14, when I tried to commit in the first transaction, this is the one that would cause a deadlock because it's trying to acquire those same same locks that this one over here had. Did that answer your question? Good questions. Any other questions so far? Yes. The question is, in what I just ran, why did this commit not have an error, not cause a deadlock, but this commit did?
Yeah, why is this first one
Question is, why is this first commit not throwing an error? If we on line 3 had a commit, why is this not throwing an error about a conflict? The answer is because the only thing that we know about right now, the only values that we know are inside of the database are the 5 and 6 from this insert up here. On line 14 over here, this 5 and this 6 don't get added until line 14 over here gets run. And line 14 might not be a commit, it might be abort, in which case if this were an abort over here, then these would not get added, and then there'd be no problems with this 6 and this 5. Good questions. The main takeaway is that the deferrable initially deferred is one of the tools that we have for avoiding these unnecessary blocks and preventing deadlocks. Problem number 3. Let's make sure we're not in any transactions on either side. Drop table T and reset my screen like this. Let's create table T, a nice simple table for us this time. Nothing special about it. Insert into T values 9. Insert into T values 10 and begin our transaction on line 4, then line 5 over here, beginning another transaction. Line 6, update T, set A equals A plus 1. And then down here, delete from T where A equals 10. And semicolon and hit enter. And you see that this command right here blocks. Number 7, line 7 over here. Oh dear. Line 7 blocked, draw a circle around that. And then line 8 back up here, commit this and it unblocks this. And question?
For some reason, we got distracted.
If the update finished before line 7, so why did line 7 right here block? The answer is because on line 6 over here, when we do update T set A equals A plus 1, this 10, this line that's inserted on line 3, we don't know whether that's going to be a 10 or whether that's going to be an 11. If we commit right here, that 10 becomes an 11. If we don't commit, if we abort right here, that 10 stays as a 10. And so this delete over here doesn't know whether to delete this line or not. It'll depend on what we do with this line right here. And extremely subtle point that this leads into is that you'll notice here that these updates and delete commands tell us how many things they modify. And this delete command right here, you can see that it's actually deleting 0 things at this point. And if I do a select count star from T, you'll see that there are 2 things in the T database, in the T table. So we should have a 2 right there next to that line 9, followed by a commit right here. So the question is that why are there 2 things right here instead of 1 thing right there? That if I do a actual select star from T, you'll see that there is in fact a 10 right here in the database. That 10 was visible to the program at the point of doing this delete. So why did it not get deleted? The answer is that the delete command or the update command, anything where there is one of these where clauses, it has a 2-step process for figuring out which rows that it's going to delete. In the first step, it finds whatever rows currently match this condition over here. At the point that line 7 is run, we don't know that this update has occurred or not occurred. So the only thing that can possibly match this is the 10 over here. It doesn't look at the 9 and then try to do the computations about the update and see what the 9 might look like in the future. It only looks at what the current values are and locks those rows for trying to delete them. And then when we do the commit over here, the row that was previously with a value of 10 suddenly got updated to have a value of an 11. It rechecks this where clause on the rows that it locked previously, noticing that it does not have a 10 anymore. It now has an 11. And so the delete here doesn't actually match any of the rows in the database. neither the 9 nor the 10 get matched here, even though the 9 converts into being a 10 and the 10 started as a 10. So this delete has no effect on the database itself. Any questions on problem number 3? Question?
Kind of related, but if you were in one transaction and have like a primary key, if your update function updates it in a way that suddenly you're not, so you have to, and then all of them become ones.
Question is, will the update command throw an error if we have a unique constraint up here and the update command violates the unique constraint? The answer is yes, unless you have the deferrable, not initially deferred statement there. That if you do not have the deferrable statement, it doesn't matter what command you run down here, whether it's an update or an insert. There's potentially other commands too that could, there are weird versions of the select and delete commands even that can add things into the tables, and those could potentially violate a unique constraint, and anything that might violate the unique constraint will cause that error immediately if you do not have the deferrable initially deferred line. Good question. Any other questions? Yes.
Why is the where clause two? Isn't it just after?
Question is, why does this where clause, why is it divided up into 2 steps? And the basic answer is that it's the only thing that is computationally reasonable to implement. That if we imagine that there were, I don't know, 1 billion rows in this table, then we would the delete clause here would have to lock all of those rows in order to wait to see if any of them in the future get updated to being the value that's inside of the where condition, and then nobody else would be able to access the database while this was blocked. So instead of being a row level lock, it would effectively be a table level lock. In this case, the update command right here and the where condition are relatively simple. So we could imagine a situation, probably what many of you did in your head was you imagined a situation where Postgres was looking into the contents of these set and where commands and doing this computation that the 9 becomes a 10. But that for arbitrarily complicated operations, in general, Postgres would not be able to do that. And so it's they don't even make an attempt to implement that for special cases. Good question. Any other questions about number 3? Number 4. I think number 3 was the hardest one on the quiz. Number 4 here, though, is the longest one. And so we will take a look at that. Lots of room here for making mistakes. Let's drop table T, no table U, there we go. So create table T, A int primary key semicolon, that's line 1. Down here on lines 2 through 5, create table U, B int references T of A deferrable initially deferred. Yes, spelled it right. Up here, session 1, line 6, begin, insert into T values 1, insert into T values 2, and then insert into U values 2. That takes me 6 through 9 up here. And then line 10, begin, isolation level, repeatable read. And again, in this case, we're not doing multiple commands that are reading from the table at all. So the isolation level is not going to have an impact. So we're on line 12 now. Insert into U values 3 like this. And here we do not have any problems on this line. We do not have any problems on line 12 because even though we have this line 3, this references right here that B is referencing table T column A. And so whatever we insert into B must exist in table T column A over here. And the 3 does not exist in that table because we have, again, the deferrable initially deferred constraint up here. That's totally okay. We'll just check the constraint at the point of committing down here. So line 12, no problems yet. Line 13 on session 1, select count star from T like that, and we get a 2 over here. Nothing, I think, surprising about that. Line 14, insert into U values 1 like this. No problems there again. We do already satisfy that constraint. Line 15 up here, insert into T values 3 like this and hit enter. No problems there. There was a potential for a deadlock situation here because we have how we're accessing the different tables here, but based on the different based on the lock levels that were implicitly acquired here, we did not have a blocking or deadlock situation. So this was line line 15 that was just executed, line 16, commit that, line 17, update U, set B equals to 5, hit enter. Notice that there is no where clause, line 17 right here. There is no where clause on line 17. And so this is applying to every row in the table because there's no where clause. Down here, now let's run our commit. And now we get an error about the update on table U violates the foreign key constraint right here. So the error messages are supposed to be X'd out right here. It's this commit right here that's violating our foreign key constraints. Down here, let's do a select count star from T, and we get a 3 over here. And then up here, select count star from T, and we get a 3 over here as well. I think I meant to make some of these counting from T's be counting from U's, but this is what I wrote. So this is the full credit answer, 2 and 3 on the left-hand side, X on 18, and 3 as the result of line 19. Any questions? Anything about the quiz? Each problem 2 points. Total it up, make sure your name's on there, please, and get those passed up to me. Any other? I can't have another meeting afterwards.
Oh, I mean, like, cut it short.
Yeah, we can cut it short.
That's it.
Question? Is that the last quiz? Yes. Yes, it was. Yay. Okay. That was the last quiz. Yes. Everybody celebrate. Question? Question is, am I considering dropping quizzes? The answer is no, but I would be open to alternative forms of extra credits. Yeah, so actually what so what I'm doing for the data structures class that I'll be close to the computer, so this is audible. What I'm doing for the data structures class that I'm teaching right now is if people complete hard LeetCode code questions, then they can use those to get points back on things that they've missed. I would like to do something similar for this class. The hard LeetCode code questions about SQL, though, are things that I consider to be easy SQL questions. And so I don't know of for example, they don't cover things like deadlocks, which are this is a hard thing right here. If anybody can find something that is somewhat equivalent, that just has problems and you work those problems, then I would be willing to give extra credit for completing those. I don't know of any off the top of my head, though. So feel free to try to find some SQL, or I would also be open to Docker or shell scripting things. And you can propose those to me as complete this and get extra credits. And I will say that, yes, that looks like a 1 point extra credit assignment, or that is a 50 point extra credit assignment. And yes, yeah, go ahead again. So there's no, in this class, there's no difference between like a point is a point, however, it's anywhere in the record. So it would just, for bookkeeping sake, in the extra credit column is where I would add the points. My general philosophy with grading is that if you can demonstrate that you have mastered the material, then you should get an A in the class. And so if you think there is a game that demonstrates mastery of the material, then I would be happy to award points for playing a game.
What is the plan?
This Friday, yeah, we won't be having any normal like Friday classes from here on out. I'll be available in my office at that time for questions, office hours sort of things. But we are on a good pace right now, so we don't need to, yeah, we're ahead enough that we don't need to do that. Good questions. Any other questions about anything? Yes.
Kind of unrelated, but
Sure.
like, when you're on April 14th, when do we not have class after that?
Yeah, so the question is, will there not be class after I go on leave? And the answer is that at that point, you'll have the final exam to work on, and I will give you a set of videos to watch with a very trivial sort of assignment going along with it. So those will take the place of like class time. But yeah, next week will be the last week of in this room class. And then, yeah, so in terms of assignments, there's the assignment to do next week, Tuesday, the Twitter inserting in parallel assignment. There's one more Twitter Postgres assignment about building these indexes, making the select queries fast. And then there'll be the final exam. Then just one last assignment for those people not graduating that'll be due after the final exam. Any other questions about anything admin or not admin wise? Okay. Last time we started talking about these trees and indexes. And the main takeaway is that trees are going to be how we reduce our runtimes down from linear in different situations down to logarithmic runtimes. So that's the advantage, and that's a huge advantage. The disadvantage, which is a mild disadvantage, is that inserts go from constant time up to logarithmic time. And we also had this sheet of final practice problems that we started going over. The first problem, you will have exactly word for word again on the final exam. The related SQL tables up here will be different, but it's just asking you to define what are the indexes that were automatically created based on these tables up here. And the key thing is that unique indexes, the unique constraint is the only thing that automatically creates indexes for us. And then the primary key up here is equivalent to unique and not null. So anywhere where you have primary key or unique, you have an index that's been created. We then talked about the internal structure of the B tree and these 4 algorithms for working with the B tree. These table scans. Here we go, the table scanning strategies. The first one of these, the sequential scan, does not require an index at all. This is always applicable. It's also always the slowest one. And then we saw the index only scan method, the index scan, and the bitmap scan. We'll review those a little bit and go over this problem 2 right here, along with some new debugging techniques for investigating what options, what index scan, what table scan strategies we have available when we're looking at a problem. So here, on problem 2, it's asking list the scan methods applicable for the following SQL query. So if it's talking about the scan methods, that's one of those 4 things about the sequential scan or the 3 different types of index scans. Always, no matter what, you always have the sequential scan available to you. So here, if you have a problem like this, you can just start off by writing out the sequential scan. And then after the sequential scan, we have the 3 different types of index scans. The first one of those, the most restrictive, but the simplest to understand, was the index-only scan. And the index-only scan, again, only looks at the index, never looks at the table at all. And so whatever information is in this query, it must be contained in the index in order to possibly be able to do an index-only scan. In this case, we're looking at the users table, and there are 2 different columns over here that we need to have access to, the ID users and the username column. If we look at our tables that we've created up here, though, that we have 2 different tables, 2 different indexes up here on the users table, but neither of them contains both the information about ID users and username. So an index-only scan is not possible for this answer. We will have to consult the table in some form. So index-only scan, not possible. Just to make that clear, I will write out index only and cross it out. It's not possible. You don't have to on a test problem cross it out like that, write it and cross it out, but I did. The other 2 options were the index and the bitmap scans. In this case, both of these will be possible. Both the index and the bitmap scans will be possible options. So why is that the case? Let's come over to our we're going to open up pSQL to our Postgres database and play around in pSQL to experiment, see exactly why that's the case. If I run Docker PS here, I have my my Postgres services running. So let's reconnect with pSQL in both instances and select count star from users, just see that we do in fact have data in here. And what else? Let's do \d on users to investigate the different keys that we have, or the different indexes that we have. On the users table, we only have the ID users, only the ID users key on the B tree. So we only have the ID users on the B tree, verifying that up here. This is a different set of SQL commands up here, a different database up here. In particular, up here, there's a unique constraint on the username column over here. There's a unique constraint on the username column, which is not present in the database that I gave you. And so in this database, there's only the ID users column. In order to make this database like the database in the worksheet, I have to create the index. So create index on users username, like that. What is the name of the field? Oh, it's just called name in here. So create index on name. And then down here, we can see that I have access to both of those indexes, and I just have to translate that over here. The column is called username, and over here the column is called name. For the final, the SQL code that you have up here will be somehow inspired by the Twitter Postgres assignments, but it is not going to be exact. There will be some differences like this about some columns having unique constraints or not having unique constraints. The column names may be being slightly different, and so you'll have to be careful about just making sure that you're understanding those, what things are similar and what things are different. Any questions about the about what is similar and different, or what I did over here? Question?
Why we can't do index only?
Question is on problem 2, repeat why we cannot do an index only scan. The answer is that in order to do an index only scan, all of the information that the select query needs up here must be present inside a single index. And here there are 2 columns that this select query needs. Inside this where constraint, we can see the ID users right here and the username column right here. So there are 2 columns that this query needs, and we don't have an index that contains both of those columns. We have 2 separate indexes that contain those columns separately, but we don't have one index that contains both of those columns in the same index. So because of that, there's no way to use an index only scan. If we had an index that contained both of those pieces of information in the same index, it might be possible to use an index only scan. We'll cover that situation in a little bit. But here we're just ruling out the possibility of index only because there's not a single index that contains both of those pieces of information that we need. So what is the index scan? Why can we do an index scan? What's going to happen in an index scan is Postgres will select one of these columns and do the index scan on that column, and then do a subsequent step of filtering based on the username. So if I come over here and type out explain select count star from users, where id users greater than, I'm going to just do a greater than 0 here as an example. Over here, when I have colon mid id users, using that SQL Alchemy syntax, this is one of these bind parameters that is going to get substituted by a user and a user of this command. And so I'm just, for debugging purposes, putting in the number 0 here as what I'm working with, and then adding these other 2 conditions down here. And username is greater than or equal to these two username conditions over here. Here, the username, it's a string, but you can do greater than equality conditions on strings. That's not a problem. And these are two separate strings over here, the min and the max. So, and I'll do username is greater than or equal to hello, and username is less than test. I think that matches, yes. Greater than or equals, there we go. And we have the column username does not exist, so it should be and name and name. That's what we typed. I'm going to do \E up here to go into Vim, re-edit this command in Vim, make it a little bit nicer looking so that it matches the same formatting as the other command that we had. And so what I've done is I've just typed this command right here is equivalent to this command over here, substituting values as appropriate for these bind parameters over here and changing the name of the column as I needed to right here. Save that, run it. I used the explain operation right here. And here with the explain operation, what we can see is that we're getting a bitmap index scan as our resulting scan strategy. The reason Postgres is selecting the bitmap index scan, we talked about before that what the bitmap scan does is it allows us to use two separate indexes, running this query on the first index and the second query on the second index, creating the bitmap of which tuple IDs are going to match, and then and that bitmap together, creating a smaller resulting bitmap and only looking in the table at the locations that match the results of those two bitmaps. So if you have an and or an or condition inside of your SQL query, the bitmap scan is almost certainly going to be the fastest thing that Postgres will select. Inside of Postgres, it's again using a bunch of weird heuristics to determine what scan strategy is going to be the most efficient. And in order to determine what other scan strategies you have available to you, what we have to do is we have to disable some of those heuristics, disable some of these algorithms, force Postgres to say that it can no longer pick a bitmap index scan, see what other things that it might pick. There is a set command inside of Postgres. You type set and then enable. These are all of the different algorithms for different operations. We've talked only about 4 of these algorithms so far. Eventually, we'll talk about all of these. And we can turn these different algorithms on and off using this set command here. So the bitmap scan is right here. If I type set enable bitmap scan equals off like this, this tells Postgres that it is no longer allowed to use a bitmap scan. And whenever it is determining what its strategy will be for solving this select query, it will have to select a different algorithm. I'll hit enter now, and we can see what that different algorithm is. It is now using the sequential scan right here. This set operation is what we call a session specific thing. So on the top session, if I type show enable bitmap scan like this, you can see that it shows that it is off. Down in the bottom session, if I type show enable bitmap scan like this, you can see that it is on. So this is only on a session by session level that these get adjusted. So we've already talked about this. The sequential scan, though, is always something that's available. I want to see, though, is an index scan something that was also available? And in order to do that, we can turn off the sequential scan like this, turn off the sequential scan, and now Postgres will not select the sequential scan as an operation. I'll do this explain again, and now you can see that we're getting the index scan as the method that it is scanning over the users table. What's happening here in this index scan is that it's using the index on the name, doing this condition on the name. And then you can see right here, it has this filter condition, add users greater than or equal to 0. After it scans this particular index, it will go through the table and complete the results, filter the results on this condition as well. So it will use the index on this condition right here, traversing on user's name IDX, index on this, this condition right here, getting the tuple IDs, and then using those tuple IDs to get all of the table information that corresponds to things that match this condition, and then apply this condition right here without taking advantage of any other index. It turns out that anytime you can use a bitmap index scan, you can also use an index scan. That the bitmap index scan is sort of the most general of the options here. There, on your next homework assignments, where you're having to create your own indexes and make things fast, this ability to determine what scanning operations you have available for different queries will be very important for you. It's also important for helping to understand or help you find the right answers for some of these problems over here. So are there any questions? Maybe as a reminder, I use the set operation to enable and disable the different scanning methods. And by default, if you're just interested in performance, you probably want all of these things enabled. But then in order to understand why, what are the different options Postgres could have chosen, you can sequentially disable these algorithms, forcing Postgres to not choose that, but to choose something else. Let's see. One of the things that's hard about this topic, and basically everything else that we'll be talking about in this class, is that it's all like extremely abstract. That the things that we're talking about many data structures here at once, many algorithms here at once, not even going into like pseudocode of most of these things, and having to keep track of when you're able to use the various algorithms and not, and what their performance trade-offs are. So it's a legitimately very difficult thing to keep track of. I want to do some variations on this problem to see what how things would be different for different variations of this problem. The first variation I want to do is I want to change this and condition to an or condition. So what would happen if instead of having an and right here, we'll have an or right here, and then we'll still group everything on the usernames to columns together with an and. So this, what I've written here, this is I guess the base problem unadjusted. But what happens if we have this or constraint right here? In order to see what's going to happen, let's I'm going to return on, so set sequential enable sequential scan equals on, set enable bitmap scan equals on. So everything is now enabled, and I will rerun this command up here, changing this to an or. And now we'll take a look at the explain results right here. We can see that we're getting a sequential scan here as the default. That's what Postgres thinks is going to be the fastest algorithm, so that's what it's going to choose. And again, a sequential scan is always something that you can use. So for the modified problem, we'll list out the sequential scan as the first thing here. But we want to see what are the other possible algorithms that Postgres could have used. So we will disable the sequential scan, set enable sequential scan equals off like this, and rerun the explain here. And you can see that we get this bitmap scan as another possibility. Anytime you have multiple of these indexes, the bitmap scan is going to be the standard thing to try to apply. here, reading this output down here, we have the bitmap index scan on user's P key, bitmap index scan on this. So these two lines right here is generating the actual bitmaps corresponding to these conditions right here. And then this bitmap ORs the results of these bitmaps together. And then the bitmap heap scan on users, scanning over users based on the bitmap resulting here, returning out all the resulting tuples. I'm going to turn off the bitmap scan, set enable bitmap scan equals off now, and see what happens. And you see that we do not get an index scan. So I have disabled everything except the index scan, but we do not get an index scan. So in particular down here, the index and the index only scans do not happen. They cannot happen over here. By changing, the key thing that I did is I changed this and clause to an or over here, and that made the index only scan something that I can no longer do to satisfy this query. Why is that the case? It's because when I was using an and clause over here, after I did my index scan on one of these columns, all I had to do was remove more things. The and clause means it's more filtering, removing more things, and that's something that we can do. But with an or clause down here, by knowing that this is something that we've filtered on, and getting a list of tuple IDs that match this, I would still have to do a full index scan or a full sequential scan of the table to match this one down here. And so there's no way of doing the index scan. The or scan, so I guess the summary takeaway message, in some sense, it doesn't matter if you understand why this is the case. You just need to understand that this is the case, is that if there's an or down here, if there's an or, you cannot do an index scan. You can only do the bitmap or the sequential scan. But if there's only and conditions down here, then you can do an index scan in addition to the bitmap or the sequential scan. Any questions about that? Okay. I'm going to modify this one more time to see how we could do an index only scan. And the modification that I will do is let's leave let's see, I'm just hesitating because I'm out of room for writing things. I want this to be an equality constraint up here instead of a greater than or equal to constraint. And then the rest of the problem is the same as it used to be. So we'll have with an and constraint right here. So the second modified problem. And I'll be writing this out, writing out the query inside of pSQL so that you can see the full version of it then. But the only difference that I'm doing is making this an equality constraint right here, and then an and right here to adjust this from the query perspective. Coming back over here, if I come back, so run this \E, change this so it's an equality constraint there and an and constraint there. If I run this as it is, it's still not possible to do the index only scan. I have to create a new index in order to do that, and create index users. The index will have to have both of this information inside of it. And so it'll look something like id users comma name, like that will be my index. Id users comma name. Create index on users id usex name. And now if I do the explain, you can see that it says index only scan right here, index only scan. So the summary of the things that I changed, added this create index. It contains both of these pieces of information right here, id users and name, and there's an equality constraint right here. If we can do that, then all 4 of the scan possibilities are available to us. And so you would write out everything. You can always do a sequential scan, and then the bitmap is the next most permissive, the index is the next most permissive, and the index only is the most restrictive. I'm going to do some variations on this to see why we're allowed to use an index-only scan here and the variations that will cause us to not be allowed to use an index-only scan. The first variation that I will do is coming up here, changing this equality back to a greater than sign. If I run that, so here we can still do an index-only scan. I guess it didn't matter what the equality or inequality there was. The index that I created before down here, if I do \d on users to list all of the information about the users table, this is the index, the name of the index that I created with id users and name. If I drop that index, so \d to get the list of \d users to get the information about the users table, come down here, this is the name of the index. I'm going to drop that index, drop name of that index, drop index, name of that index. And up here, it's no longer going to be able to use the index only scan, only an index scan is available. And I'm going to create the index, create index on users, id user on users, name, id users, putting them in the opposite order like this, putting them in the opposite order. If I put them in the opposite order, what's going to happen is that it will no longer be efficient to use an index only scan. The reason for that is coming over to, we're going to take a look at the B tree structure internally, how it is going to store the information when you have multiple tables inside of the index. So this documentation is again looking at the haber.com link, and we saw this table or this figure of a B tree index previously, where each of these inner boxes right here, the 4, the 32, and the 64, are the values of an individual key. If we come look at this picture right here, which is just scrolling down a little bit in that table. Here, this is a picture of what an index looks like that has two columns inside of it. We have the 1 and then a numeric column, and then a string column representing a type of airline here. And the information down here is going to be sorted in order first of whatever the first column is that you type in, and then subsequently sorted based on the second column. So here you can see the first column here, the 1s and then 2s and then 3s, those are sorted alphabetically, numerically. Down here, the names of the second column down here, Bombardier, Cessna, Sukhoi, those are only sorted alphabetically in the same context where the first column is equal, where the 1s are equal, the names of these airlines are equal. But then when we go up to 2 here, the Airbus, we start over alphabetically, getting Airbus at the beginning, then Boeing, and so the alphabetical sort only happens after the way that Postgres breaks ties in the sorting on the first column is by using the sorting of the second column. So coming down here, if we have the name and the id users, if things are first sorted on the name and not on the id users, then doing an equality search on id users is not an efficient thing to do, because the id users can be stored anywhere in this in the index. I don't know, I feel like the last couple minutes very fast through some of the stuff about indexes with the multiple columns, but questions about that? The key thing that you'll want to make sure that you're able to understand is these this figure right here and how it compares to this figure up here in order to know how the column information is being sorted. We're pretty much out of time though, so next week we'll continue doing more of these examples, continue going through the notes over here and these other algorithms. If people have questions, I'll stick around and answer them. Otherwise, I will see you all next week.